Hello, welcome to our talk about ROCm, AMD's platform for GPU computing. My name is Pavel Pomorsky and my contact information is there if you have more questions. So to motivate this talk a little bit, we have mostly been using NVIDIA GPUs in our clusters for the last few years, but we have also been trying to keep up with what AMD is doing in their GPUs. And to do this, we have acquired a single node with some gaming AMD GPUs in it, and we wanted to test it, see what is the latest hardware and the latest software that AMD has. And this is where this talk is building, what this talk is building on. So to run GPU software on AMD GPUs these days, you need ROCm. So what is ROCm? It stands for, it's AMD's open source software development platform for GPU computing, HPC GPU computing. It is essentially an alternative to NVIDIA's CUDA. It does the same things that CUDA does. It was launched as under the name of Boltzmann Initiative in 2015, and I think it went through another name change, but now it's ROCm. And one of the goals of ROCm is to enable easy transfer of code between GPU architectures. So code developed under ROCm will be able to run both of NVIDIA GPUs and on AMD GPUs, which is a huge plus because CUDA is confined to run on NVIDIA GPUs only. And also for AMD, it offers an easier alternative to OpenCL, which has proven somewhat hard to use for people. So ROCm is a huge set of programs, and I will only list some of them here. So it includes runtime and kernel drivers, so software to actually talk to the GPU, includes an OpenCL driver and compiler, so you can use OpenCL within ROCm if you want. Importantly, it includes the HIP compiler tools, and I'll be talking a lot about those. So this is what you actually write your software in when you're using ROCm. It contains a rich set of libraries, BLAS, RAND, FFT, sparse, things you would expect. It also has a debugger and a profiler. So, before I talk more about ROCm, let's do a little bit of an overview of what kind of AMD GPUs are out there. So I found personally that understanding this for AMD, it's harder than for NVIDIA's GPUs. AMD seems to have a greater variety and they are named in more confusing ways. But I try to distill this information as much as possible. And here I am listing the latest 4 families of AMD GPUs, which we currently have. So AMD, as you well know, is the main competitor in NVIDIA. Just like NVIDIA makes gaming GPUs, AMD makes a lot of gaming GPUs. The family names are complicated, but they fall under the following: Arctic Islands, Polaris, Vega, Navi, and Arcturus. So these are the years they were released. So the names matter less than these codes. So each GPU has a code which is analogous to NVIDIA's compute capability code. And this essentially designates an architecture of the GPU. So we have GFX 8, 9, 10, 11. And I'll say more about this one in a second. And then the instruction set also changes. So these are the last 4 generations. And these are basically gaming cards, the first 3 rows mostly. And then the last fourth row is special. This is the new AMD's Tesla analog GPU. It's called MI100. So, but here's one very interesting thing I found about ROCm, that whereas CUDA is supported on pretty much every single GPU that NVIDIA makes, so if you buy any GPU from NVIDIA, you can install and you can run CUDA on it. This is far from being the case on AMD. In fact, ROCm is only supported on a selection of AMD GPUs. And in particular, the older generations, GFX 8 and GFX 9, they do have cards which are supported. And even within a single architecture of cards, it's not a given that all of them are supported. So you have to always double check. But the interesting and unfortunate fact that for the Navi generation, which is the latest, the Navi family is the latest set of AMD GPUs, this is their main GPU line. Unfortunately, ROCm is not fully supported. So I put a star there because officially it's not supported, but in practice, to a certain extent it is, because we have been able to test ROCm programs on Navi cards. And apparently full support for ROCm on Navi cards is promised by about the middle of 2022. So that appears to be on the way. So this means that we can sort of use those cards for testing. And those are the cards we have in our test machines. So we will sort of be able to use them for testing, but there will be some issues that I will discuss. And the interesting thing here is that one very interesting thing is that AMD has diverged their architectures for gaming and for computing. So whereas the Navi cards, GFX 10, GFX 11, this will be the branch for gaming, there's now also a branch for computing. This is the CDNA architecture. So RDNA is gaming and CDNA is compute. And that will have codes GFX 908 and so on. So there's this paradox that even though even though this is the latest card, its code seems to go back to the Vega generation. And the dot dot here just means that there's additional numbers. So it's like GFX 904. Those are the typical codes. So AMD does have this issue that there's a huge family of their latest cards which don't fully support ROCm right now, which is something that you have to keep in mind. Let me also talk about the high-end AMD GPUs and what the landscape is there. So, if you are interested in high-performance computing, you would probably not be buying gaming cards, even though, interestingly enough, AMD has no problem with people buying gaming cards and putting those into their servers. So NVIDIA has this clause that you cannot put a gaming card into a server, but with AMD, that problem doesn't arise. So, but here's a list of the proper AMD server cards. And here AMD has been lagging behind NVIDIA. So NVIDIA has really been dominating the HPC high performance computing GPU market for a long time. So with their Tesla line, so Tesla from NVIDIA, those are the cards which go inside high performance computing centers. So the first competitor to Tesla that AMD released was the family MI6, MI8, MI25. These came out around 2016, 2017. And these were only cards which have single performance enabled. So a single precision enabled. So you can do double precision on them too, but at a huge performance hit, like a factor of 16 slower. So they're really only good for single precision, whereas Tesla has been supporting double precision for much longer. And then the next iteration of the Radeon Instinct cards is MI50 and MI60, came out in 2018. And these fully support double precision, so no problem there. And those are nice cards. And the latest card from AMD is called MI100 that came out last year. And not only does it is it bigger and it supports double precision, but it also has matrix cores. So matrix cores are the analogs of tensor cores that NVIDIA has had in their GPUs since the V100 Tesla generation. And by the addition of matrix tensor cores, these cards become competitive in machine learning, deep learning application with NVIDIA GPUs. So you can basically see from this that AMD is catching up to NVIDIA in terms of features that are available on their cards, which of course is another incentive to study the software that AMD provides for programming these cards, because these could actually be GPUs which you will be buying or which we will be buying in the future. And upcoming is MI200, which is a further improvement on MI100. And not only this, but AMD, because they make both CPUs and GPUs, they have long had a line of what are called APUs. So APUs are chips which combine a CPU and a GPU in one chip, sharing the same memory. And this has been available for the last 10 years, but only on the consumer side of the market. But what's coming soon in a year or two are proper high quality HPC APUs. So you will have CPU and a GPU on the same chip. And the advantage of that is that you then don't have to worry about the bottleneck for memory transfers between the GPU and the CPU, which for certain problems, it's a huge issue because if you have a GPU and a CPU and you want to offload some work from the CPU to the GPU because it runs faster there, this offload only makes sense if the time it takes to transfer the data is significantly shorter than the time you're spending computing, right? And for certain problems, that's true, but for a wide variety of problems, it isn't true. And that means that you couldn't do them on a GPU connected to the CPU through a relatively slow link like the PCI Express link. But once they're on the same chip and they are actually sharing the same memory, the memory transfer problem disappears because no memory needs to be transferred. So this is another reason why AMD hardware is potentially interesting. So let me talk a bit about the actual experimental node we have on Graham right now, and we have not fully set it up, but hopefully once we iron out all the kinks, this will become available to all our users, so everybody will be able to test their software there. So this node, which is just a node on Graham currently, has 8 Radeon RX 5700 XT GPUs. So these were released in July 2019. They are relatively new. They are high-end gaming cards. I just checked their price online right now, and of course, GPU prices have gone up, and they are each about $1,500, so they are pretty pricey. The cores, they offer 2,560 cores, and these are gaming cards, so single precision only, double precision will not do well there. And the architecture is Navi 10 and RDNA, as you would expect for the latest gaming cards. It's Navi, and that means that we don't have official ROCm support on those cards, but we have partial supports. So some things will work and some things will not work. There's actually kind of a difficulty there, because if something is not supported, you don't really know what combination of kernel, Linux, and driver will work best. You have to consider, for example, actually there's a specific issue with ROCm, is that it has 2 sets of drivers. You can use the GPU drivers from ROCm itself, so ROCm comes bundled with drivers, or you can use upstream GPU drivers released by AMD. And they both have disadvantages and advantages and disadvantages. It would appear that ROCm supports newer GPU features, and the upstream driver supports newer kernel features. So in a sense, and because there's no official support, we don't know which one is better. So we have been trying various combinations. And at least at this particular point, we don't have a working driver on the AMD GPU node yet, but we are working towards it. But to get some results for this talk and to play around with the GPUs, I found that using GPUs on Amazon Cloud is a good alternative. So on Amazon Cloud, there's one flavor of virtual machine which offers the Radeon Pro V520 card, which is actually very similar to the card we have on Graham. It's much newer. It's released in 2020. It's only a cloud. It's a cloud-only offering card, so I don't think you can buy it. It's only available on clouds. Has about the same number of cores, 2300 architecture. It's a little bit newer, but it's still Navi and RDNA 1. Same situation of ROCm support. But the nice thing is that AMD, AWS, Amazon Cloud, they have a bundle of drivers which they offer for installation. And I would assume that these drivers are probably more reliable because, well, millions of people use Amazon Cloud and probably thousands of people use these instances. So I would assume these drivers have been fairly well debugged. And this is probably why I was able to get ROCm to work on this virtual machine. Another nice thing about the virtual machines like this is you have a lot of flexibility. You can create and tear down virtual machines very quickly. If something doesn't work, if you made a mistake in the installation order, you just destroy the machine and start a new one. This is harder to do in an HPC cluster because there you need a sysadmin to repave the node with a new image, which will not be done instantaneously and involves multiple people. So at least I found that using AMD GPUs on the cloud is nice. And I think it's cheap. It's this machine officially costs something like 50 cents an hour. So of course I wouldn't run any production jobs at that price without some serious thinking about it first. But if you're just doing quick development, building virtual machines, which doesn't take that much time, it's not that expensive. And I don't even know whether what I am doing falls under their free usage limit. Maybe it does, but definitely don't quote me on that. But I would say that if you really want to play with AMD GPUs quickly, AWS Cloud is a really nice option, and I would encourage that. So ROCm is a very complicated set of packages. It's essentially a giant bundle of all these different tools. So if we were to install it on our environment, it will be quite painful because we don't have a standard Linux distribution. We run CentOS, but that's only the bare CentOS to run basic things. And then the actual software libraries are installed in the CVFMS directories, which is highly non-standard. So building ROCm under our environment from source would be a huge undertaking. It's not impossible, there do exist scripts for building ROCm in various Linux distributions. So we would presumably have to modify those, but it wouldn't be easy. So we decided to instead use a Singularity image, which my colleague Paul Prini, he did basically all of the work to make those images, and I thank him for that. And once you make a Singularity image, as you will see, in a Singularity image, you're seeing just a standard Linux distribution. So you can install all your software there. And then, of course, you have to ensure that the host on which you're running the Singularity image on has working drivers, which we haven't gotten to yet, but we do have a Singularity image. Now, one really beautiful thing about the Singularity image is that you can have a single image which is configured to both work on machines with NVIDIA and AMD GPUs. Because as I mentioned, ROCm can work on both. So even if most of our cluster, except this one node, uses NVIDIA GPUs, we could still install ROCm and have people use it for the Singularity image. And I will show you an example of this. But again, the key thing is you must have working GPU drivers. So on a NVIDIA node, we already have CUDA drivers, so everything works perfectly there. But on the AMD nodes, we'll have to figure out the right driver combination to actually get it to work. So this is just a screenshot of how Singularity works. So here in this example, first, I am on the Graham 1339 node, which is the AMD node. And we have Singularity installed there because that node is actually using not using our standard image. And then the Singularity image is here, ROCm with the .cif extension. And here I can use a switch --app, and I can decide whether I want the ROCm flavor of the image or NV flavor. I also mount my home directory, and this flash --ROCm is necessary to enable interface with the drivers on the host. So once I do this, I get a bash prompt within Singularity, and here I can run ROCm commands. So in this example, I ran hipify, which, as I will explain shortly, it's a tool to convert CUDA code to HIP code. And then I run hpicc, where I compile my resulting HIP code. And then I try to run a.out. In this case, it wouldn't work because we don't have the drivers yet fully working on that node. And with exactly the same image, here's what I would do on NVIDIA node. So I load the Singularity module, I haven't shown that step. And then I run the same command, except now I do a switch where I launch the CUDA version of the image. And the --nv means I'm connecting to the NVIDIA drivers on the host. And here again, I have access to all the command line ROCm tools. And the program which I compiled here, I can run it and it works. And as I'm showing here, I'm running this through NVProf. So what ROCm does is when you compile for NVIDIA, and by the way, with this switch, I have basically set all the environment variables so that compiling for NVIDIA becomes the default. This is why I did not have to specify anything specifically saying compile this to NVIDIA. It will just happen automatically, which is quite convenient. And the executable which I get, a.out, I can run it through NVProf, and it runs. And the HIP executable created by hipcc is basically just a CUDA executable. So all the CUDA tools just work on it as you would expect. So this is how Singularity works on our clusters. And if we ever install ROCm on them, it will probably be this kind of arrangement. So let's talk about HIP more specifically. So what is HIP? So this is the main way to program GPUs in ROCm. And HIP is a C++ dialect, which is very similar in syntax to CUDA. So it's basically C++ with extensions. And the HIP code can be compiled to run both on NVIDIA and AMD GPUs. So in the example that I've shown you before, just to be clear, the source code here is exactly the same. It's just a CUDA source code, which I convert to CPP, and I compile it on an AMD machine, a machine with AMD GPUs, and a machine with NVIDIA GPUs, and it's exactly the same code. It's just a different executable with results. So HIP provides a strong subset of functionality in CUDA. So it doesn't support all features of CUDA, so you can't take every CUDA code and convert it to HIP. So some features are not supported. For example, dynamic parallelism isn't supported. Float 16 is not, and the list continues. Some of this might change. I mean, support for some feature might be added in the future. So that's a possibility. But at the same time, most CUDA codes are written, they don't rely on these advanced features. So for most CUDA codes, in quotation marks, this strong subset idea will work, that you will be able to convert your CUDA code into HIP code. And HIP code provides the same performance as native CUDA code. So there's this close, so basically HIP is CUDA, just with different syntax. That's one way you should think about this. But it also provides the benefit of running on AMD platforms. So you could make this argument that if you're a CUDA developer, you might consider just switching into HIP code, and you will still be able to compile for CUDA without any problems. But now you will also have the option of running on AMD platforms, which could be considered a win. And the correspondence between CUDA and HIP is so close that there's an automated tool just to take your CUDA code and to convert it to HIP code. It's called Hipify. Interestingly enough, there isn't a tool to go the other way, which, I mean, you wouldn't expect ROCm to provide a tool for that, but probably it would be pretty easy to write, so you would be able to go back and forth. So to make it more specific, let me just compare HIP and CUDA syntax. So I'm just putting the HIP command above and the corresponding CUDA command below. And you can see that the syntax is pretty much the same. It's just there's a name change. There's a HIP malloc and there's a CUDA malloc. That's exactly the same except for the name change. HIP memcopy, CUDA memcopy, and then the kernel launch is a little bit different, but the arguments are pretty much the same. There seem to be additional arguments here for the kernel launch, but those are actually arguments which you can also give to the CUDA kernel launch. So it almost seems that the main conversion is to get rid of any appearance of the word CUDA, because that's copyrighted or trademarked, and to replace it with HIP. But otherwise, the syntax is almost exactly the same. So you can see that HIP, it's almost like a kind of a macro conversion of CUDA. That's all it is. So the two codes are pretty much exactly the same. And then within the kernels themselves, the kernels are actually exactly the same. No change whatsoever. So this makes it even easier. And in some older documentation, you can see that instead of threadidx.x, one had HIP threadidx_x, so they changed the name a little bit, but then they just decided that it's not worth it. They're just using exactly the same syntax as CUDA does, which is really pretty convenient. So that means that if you have some CUDA GPU code, the change from one to the other is really simple. You're not changing your kernels, you're just changing your API functions a little bit. So now I actually want to show you an example of an actual code which isn't that sophisticated, but which does push the GPU a little bit in terms of performance. And then I will show you what kind of performance numbers I get from both HIP and CUDA. So I'll be looking at matrix multiplication, just a matrix multiplication of square matrices. So just as a review, the way that works is to compute the final element of matrix C, which is the result. You need to take the corresponding row times the corresponding column, and then do an element-wise multiplication and add the results. So if I was writing a naive kernel to do this, I would just have this. So I would have one thread handling each element of the matrix, and each thread would then do a sum where it takes the row and multiplies it times a column. So you could call this simple or naive matrix multiplication. And this will give the correct result, but we would expect for it to perform very badly, as we will see. One major reason for bad performance is cache misses. This has a really bad cache usage pattern. So one simple way to fix this up is, so let me go back to the picture. Let's now imagine that these are not individual elements of the matrix, but these are 32 by 32 blocks. So I have a block of threads, and each block of threads is handling a block element of the matrix. We could take a block element and copy to shared memory. And shared memory is this fast memory right on the multiprocessor of the card. And we could go block by block. So we could copy this block and this block to shared memory, do the multiplication, store the result, and then copy a new pair of blocks into shared memory, store the result, new pair of blocks, store the result, and so on. And the advantage of this is that we have a very orderly pattern of access to memory, where we are copying the entire block before using it into the shared memory, which is essentially the L1 cache. This is the fastest cache on the GPU, and accessing from there. So basically our cache misses will drastically decrease by doing this. And the code which does what I just described in the pictures is this one. So it's a little bit complicated, but the idea is fairly straightforward. Essentially, there's a preliminary step where I have each thread copy one element that it's responsible for in the two tiles in the AMD tile into the shared memory. And here I have a shared memory region defined. And then I do a sync thread. So I put a barrier to stop there until all the threads have finished their copying. And then I have each thread compute the partial sum on that tile, but only accessing the shared memory region. So that will be much faster. We will not have cache misses when we do this. And another sync thread has to be given here because once a thread has finishing its sum, it has to stop and wait until everybody else has finished before it tries to modify the elements in the tile. So this is just, as I said, the kernel code is the same in HIP and in CUDA. So both HIP and CUDA code would actually have the same syntax. And here's the results. So I tested this on the AWS machine on the cloud. So this is Radeon Pro 520V, has 2,304 cores. And the comparison here is a Tesla P100, which is a card that's the most common card on Graham. It's about 5 years old at this point, so it's actually not the latest. It has 3,584 cores, and these are the theoretical maximums quoted for these cards. So they are roughly comparable in performance. Tesla P100 is a little bit faster. But anyway, so the interesting numbers are the simple code. So the naive code takes 4.98 seconds on the Radeon, and the improved code goes down to 1.34. And the simple code takes about 5.21 seconds on the Tesla, but it goes down by a huge factor of 10 once you switch to using shared memory. And just for comparison, once you actually use a proper library, once you use the cuBLAST library, you can go down to 0.144. And you can see that once you use the cuBLAST library, then you're approaching the theoretical maximum performance of the card. Whereas in the other case, you're not even close. And that's to be expected because we are trying to beat a library. I mean, a library will have very sophisticated code, whereas our code is quite simple. But the upshot of this slide is, well, first of all, the performance of the AMD and the P100 card is comparable. I mean, these are GPUs that they will offer similar performance, broadly speaking. But what is interesting is that the gain that we get from the using shared memory is quite different. So here we have a factor of 10 gain, and here we have a factor of 3 or so gain, right? So I guess the point I'm making is that you can easily convert CUDA code to HIP code, but that simple conversion doesn't mean that you'll get fully optimized code because the AMD architecture in the GPU is different from the NVIDIA architecture in their GPUs. Underneath, they are different. So if you are actually writing HIP code in real life and you want to optimize it, you will have to have forks where you have different code running on different GPUs. You will probably have to tweak block sizes or things like this, for example, at the minimum when you're launching on the AMD and on the NVIDIA card. So even though the code is meant to be portable, it isn't truly portable. So clearly the Tesla code is much better optimized than the AMD code. So there's some optimization step that we have to add to actually make competitive AMD code in this case. And I couldn't test the BLAST library on AMD. So BLAST library is part of HIP, and actually HIP-CC, when it sees a cuBLAST library, it will automatically convert it to use the BLAST library in HIP. So that's really, really nice. So it doesn't just convert code automatically, it converts libraries automatically. But the problem is that the BLAST library, because it has specific tuning for specific GPUs, it just doesn't work on not supported GPUs at this point. So it will just refuse to work on the GPU which I had on Amazon Cloud. ROCm comes with a profiler. So as you have seen when I compile my code for NVIDIA, I can, what I get is NVIDIA code. So I get the performance is the same. It's literally just NVIDIA code. So I can run the NVProf utility on it. But if I'm providing for AMD, I need a specific utility which works on AMD, and that is ROCprof. Unfortunately, to do proper profiling, you also need full driver support, which we don't have. So I couldn't do full profiling with this tool because the performance differences that we are seeing here, they probably have a lot to do with cache misses and how many cache misses you have. And you can extract statistics on this. At least you should be able to, with a proper profiler, you can actually count how many times you miss the cache, and you would be able to understand the differences in performance better. But unfortunately, on the card I was using, that's not enabled. So the way ROCprof works is you can provide as input an XML file where you can give a very detailed specification of the kind of metrics you want to collect. You can be as specific as you want. And but unfortunately, to collect these metrics, you need to have a supported driver. ROCprof is a little bit user-unfriendly in that the output is in CSV format. So you just get a CSV file with all your metrics. So you have to use some additional software, maybe a spreadsheet or something like that, to actually conveniently view that data. So it's a little bit less user-friendly than the tools you get, the profilers you get from NVIDIA. But again, the key thing is to have a GPU which is supported by ROCm. So to change gears a little bit, I did actually want to run some software on a GPU properly supported by ROCm. And it turns out that one of my colleagues, Armin Sobani, has access to a test cluster that AMD provides to selected developers. And I hope to get access to that cluster soon, but I wasn't quite able to do it for this talk. And on the cluster, we have the latest MI50 and MI100 GPUs. So I asked Armin to run a small set of benchmarks to see how those cards perform. So in general, a whole set of popular scientific software has been ported to ROCm. And if you want to see the most popular packages, they are available at AMD Infinity Hub, so you can check that out. What I did in my case is I went straight to the NAMD page. So NAMD is a popular molecular dynamics program, and MD programs generally work very well on GPUs. And then they do offer an alpha version of their latest build where you can get a ROCm supported binary and source code. So actually the binary which they offer is built against an older previous version of HIP, which actually turned out not to work. So I built it from source, I targeted the right architectures, and I got an executable that works. So I'm not sure whether this is optimal. It seems to be a little bit outdated. In particular, I'm not sure whether this fully supports the MI100 card, but at least I was able to get a code which runs. And here are the results. So this is the most popular STMV benchmark, which is the standard benchmark for NAMD. Here I was using 16 CPU cores and 1 GPU core. And the results are, they are basically all the same ballpark. So steps per second, this is a number where higher is better. So the MI50 and the P100, they have basically the same performance. And the Tesla T4 card, which is a little bit newer version of Tesla, which is single precision only, is about the same. If you want to see what software is available, I definitely suggest checking out AMD Infinity Hub. So we are approaching now the last slide, and I will also mention that, as you would expect, machine learning is fully supported within ROCm, and PyTorch and TensorFlow are available for ROCm with upstream support for easy installation. So basically, once you get through the hurdle of installing ROCm and getting the drivers working, installing PyTorch and TensorFlow, it's very simple. It should just be a pip install operation. And ROCm also offers a rich set of libraries with high performance machine learning primitives. Now, if you have an older card or a Navi card which doesn't fully support ROCm, it should also be noted that just using OpenCL, which is this older, more basic interface, is still a possibility. I have seen people, I haven't tried it myself, but I have seen people using only OpenCL to run PyTorch and TensorFlow. So in terms of performance that you would get from deep learning, one thing which was holding AMD back is they did not have tensor cores until the MI100 card came out about a year ago. So tensor cores are specialized circuits on the GPU, which are specialized in doing low precision calculations, and lower precision calculations are a very good fit for deep learning workloads. But now with the MI100 GPU, AMD is catching up, and that will be the trend in the future. So that's our experience with ROCm. It's a work in progress. We expect to have more machines to test with, and we expect to resolve our driver issues. And we hope to have an AMD machine available to you for on Graham for testing in the near future. Thank you.